we start with the simplest possible case where you have motion only in one spatial dimension. You have one particle moving in one spatial dimension. So let's just talk about the general setup from which we start. So we have the general equation of motion in one dimension, and that is simply mass times acceleration. And now this is no longer a vector, but we just have a single component, x, a single dimension. And this is given by the force, which in turn is a function of x of t, the velocity at time t, and possibly explicitly also on time t. If, for example, you have a driven harmonic oscillator, then you have an explicit time dependence. Let me give you a few very simple examples that often occur in problems and also in nature, of course. That's why they are important. The simplest case is that you have no force at all, so you have free motion. The next, also very simple case is minus mass times gravitational constant, and this describes a homogeneous gravitational field. So that's what you assume to describe a particle falling from a tower, for example. So this is a homogeneous gravitational field. Another possible form for the force might look like this. It's as before, but there's an additional term, gamma times x dot, and you encountered such dynamics also in your first problem set that was used to describe friction, say in a medium. If you have a body falling from a tower here on Earth, then you have resistance from the air. So strictly speaking, you don't have minus mg, but you also have a friction force that comes from the air. And that you can describe that, sort of the simplest way to describe that is with a term like that. It's a velocity-dependent friction force. So that would be a homogeneous gravitational field with friction. Then you might have a law of force, which is minus some constant times x, the position. It's Hooke's law, and it describes a harmonic oscillator. Yeah? It's a mass appended to an elastic spring. So it's a harmonic oscillator. And then to give you just an example of a force that may depend explicitly on time, think of a force like that, minus kx, plus some constant times cosine of omega t. So you have an extra term that's proportional to cosine omega t, and that would be a driven harmonic oscillator. Now, to make life even simpler for us, we would like to focus here on forces that are not explicitly time dependent and also not velocity dependent. So that's really the simplest you can get. So here we focus on the case F, force as a function of x and x of t. So no explicit time dependence and no velocity dependence. This is the setup for the simplest case that we want to study. Now look again at this equation of motion. One thing we can do is we can multiply this equation of motion on both sides with the velocity. So we can multiply this with x dot on both sides. And then you recognize on the left-hand side, this is nothing but the derivative with respect to time of m over 2 x dot squared. You see that? And that's the left-hand side. And on the right-hand side, you can write that also as a time derivative. You can write it as minus d over dt of some function u of x, where u of x is defined as minus the integral. The lower bound is unspecified, can be in an arbitrary lower bound, but the upper bound is x, dx prime f of x prime. So in particular, you have the property d over dx, so the derivative of u, that is minus f of x. And you may, in the definition, you may also include an arbitrary additive constant. Now you recognize on the left-hand side, what is this here? M over 2x velocity squared. Exactly, that's the kinetic energy, which I would like to denote by T. And this function u is the so-called potential. Yeah, this is the potential. So what immediately follows from this manipulation is that the time derivative of t, and now I can take the potential to the left-hand side, t plus u, vanishes. And therefore, t plus u is a constant. And this is our first integration constant. We said in our general recipe that when we solve the equation of motion in spatial dimension d, we expect 2 d integration constants. So if d is equal to 1, we expect 2 integration constants, and this is the first of them. It's the sum of kinetic energy and potential, or potential energy. This sum is a constant of the motion, and it's our first integration constant. So this is the total energy. The sum of kinetic and potential energy is the total mechanical energy. And this reflects energy conservation. Now, with the help of this first integration constant, we are ready to approach the general solution. Let me rewrite this energy conservation in the following form. I can say that the kinetic energy, which is m over 2 velocity squared, this is the total energy, which is a constant, minus the potential energy, which is a function of position only. we can solve this for the velocity. We can say the velocity x dot, this equals, now this is then the square root of 2 times e minus u of x divided by m. So we have a formula for the velocity. And x dot, of course, is dx over dt. And you see we have now a first order differential equation for x of t, and it's a separable first order differential equation. So we can write that as dt, we take dt to the left and the square root to the right, and then we have dt is equal to the square root of m divided by 2 e minus u of x dx. And to solve this equation, we simply integrate on both sides. So I can give it a prime here, and then I can integrate from t0 to t, and on the right-hand side, I integrate from x0 to x. And I obtain, on the left-hand side, this is t minus t0, and on the right-hand side, I have integral from, let me write it again, x naught to x dx prime square root of m over 2 times e minus potential at x prime. And this x naught, that is the initial condition for the position. That's the position at time t naught. That's our starting time. And this is our second integration constant after the energy. That's the second integration constant. Now, this integral gives us t as a function of x, and also dependent on the two integration constants, namely the initial condition for the position and the energy. These are our integration constants. This is almost what we want. When we want to solve the equation of motion for a mechanical system, of course, then we would like to find the trajectory. We would like to have position as a function of time and not time as a function of position. Therefore, we still have to invert this solution. So we invert this, and then we obtain x as a function of time, and then also dependent on the initial condition and the energy. And this is the general solution. So this is the basic logic, how you proceed to solve a mechanical problem in one dimension. I would like to show you how you can visualize this a little bit graphically, and I would also like to focus especially on periodic motion and how you can calculate the period of periodic motion if it is periodic. Let me sketch as a function of position x. Let me sketch the potential energy U of x. Let's assume the potential has a shape like this. Yeah, so this is U of x. And let's assume that the total energy, which is one of the two integration constants, has this value here. So this is E. And let's further assume that the initial position of my particle, of my system, is here, x naught. So E and x naught are the integration constants. Now, at a certain position, now let's start with x naught initially. That's where the particle is initially. What is its kinetic energy? The distance between the green line and the blue curve, exactly. So this distance here, this is the kinetic energy. Now, the kinetic energy is non-zero, which means that the particle has a non-zero velocity. So the particle is moving. It's not clear whether to the right or to the left, but it's certainly moving. What is the sort of the extreme point that the particle can reach when it moves? Exactly. That's where the two curves, the green line and the blue curve, where they intersect. These are the extreme points that the particle can reach. Let me call these extreme points x1 and x2. And what's going to happen is, let's assume that initially the body moves to the right, then it will reach the point x2, and then it has sort of consumed all its kinetic energy. Kinetic energy is zero there, cannot go any further, and then the particle will turn and will go back to the left and will swing to the left extreme point, x1. Again, it cannot go any further because there it has velocity zero, cannot go any further, and it will return and swing back and forth. So you will observe periodic motion between the two turning points. Yeah, so these are the turning points, and you expect periodic motion. Now, motion in 1D doesn't necessarily have to be periodic. It really depends on the shape of the potential, and it depends on the total energy. So if you have a free fall, this is clearly not a periodic motion. Yeah? But if it looks like this, then you have periodic motion. And one question that we will also encounter now on the new problem set, it's the first problem on the new problem set, is that you are given the equation of motion for a one-dimensional system. The dynamics is, or the motion is periodic, and you are asked to calculate the period of this periodic motion. So how can you calculate the period? Go back to the previous page and remember this expression here for the time difference, t minus t naught. That's the integral from x naught to x, dx prime, and then the square root. If we take as the lower bound of the spatial integral on the right-hand side, we take the left extreme point, and as the upper bound, we take the right extreme point, then what you have on the left-hand side is precisely the time that the system needs to go from the left to the right extreme point. Now the period is defined as the time that you need to go back, to go from left to right and then back to the left, so you get an extra factor of 2. So with this logic, you find a formula for the period, capital T. This is 2 times the integral, as we said, from the left extreme point to the right turning point, dx, and then, as before, the square root of m over 2 times e minus u of x. So this is because you have to go back and forth. Let me move on to still a single particle, but now in 3 dimensions. We're no longer constrained to 1 dimension. And now this is pretty trivial. When you have a single particle, a single body in 3D, that's where we are. And you know the change of its momentum is given by the force. This is the second axiom. And then this immediately implies, now this is very trivial, if you have no force, say because it's the only body in the universe and there's no other body to exert any force on it, then this implies that the momentum is constant and the motion is uniform. This is just for the record, it's nothing new really, but just for completeness I wanted to add that. Let's move on to a more interesting concept, and that is the concept of angular momentum. This is something we have not yet introduced, but I'm sure you know what it is. The angular momentum of a particle, of a body, is defined as its position, vector, cross, vector product with the momentum. That's the definition of angular momentum. You can also define the so-called moment of force, or in German that would be Drehmoment, and that's defined as position vector product with the force. Now we can consider the change of angular momentum. How does angular momentum change in time? So we take the time derivative of L, looking at the definition. We have product rule, so we have R dot cross P plus R cross P dot. Now what can we say about the first term? The first term is velocity cross momentum, but velocity and momentum are parallel, and the vector product of 2 parallel vectors vanishes. Yeah? So this is 0 because R dot is parallel to P. And in the second term, we know P dot, this is nothing but the force, and therefore we find that the change of angular momentum is position cross force, but that is what we had just defined as the moment of force. So we find the rule that the change of angular momentum is given by the moment of force. In particular, this implies that if, again, say the body is the only body in the universe, and there is no force acting on it, and then in particular there's also no moment of force acting on that body, and this implies then that the that was a mistake. Then this implies that the angular momentum is constant, and we have conservation of angular momentum. But we will see shortly that the body doesn't have to be alone in the universe to have no moment of force acting on it. This also applies, for example, if the body moves in a central potential. So the situation where you have no moment of force occurs more frequently in nature, and therefore angular momentum conservation is something that you often have in a mechanical system. Yeah, talking about the central force, let's move on to define what that is and what consequences it has. Now, let's consider a body here with position vector r with respect to the origin of our reference frame. And there is a force acting on this body, and the force is called central if the force is parallel to the position vector. So it points towards or away from the origin of our reference frame. Yeah? So let's say the force points in this direction. It might also point in the opposite direction, but it certainly points along the axis spanned by the position vector. So central force means force vector is parallel to position vector. Now this immediately has an interesting consequence. If the force vector is parallel to the position vector, this implies that the moment of force exerted on the body, which is r vector product with f. Now since r and f are parallel, the vector product vanishes. So the moment of force vanishes, and therefore the angular momentum of our body is conserved. At the same time, we know the angular momentum is position vector product with momentum. This implies that the angular momentum vector is orthogonal to both the position vector and it's orthogonal to momentum. Now, given that the angular momentum vector is constant, or in other words, let me rephrase it in the following way. Position and momentum, they span a plane which is perpendicular to L. Now, if L is constant, then this implies that this plane spanned by position and momentum must also be constant. So the orientation of the plane must be constant in time. Yeah? So L is constant, therefore the plane spanned by R and P is constant. And this implies that position and momentum, and therefore also velocity, will always lie in the same plane. Yeah? So R and P always lie in the same plane. So let's say, for example, here that our body has a certain momentum pointing in, let's say, this direction, P. Then R and P will span a plane. Let me try to indicate it like this. Yeah. This is a two-dimensional plane spanned by R and P. Now, according to the right-hand rule for the vector product, the vector of angular momentum is perpendicular to that plane and will point sort of will come out of the screen. Yeah. So the I don't know if you're familiar with this notation here with this dot. This is the angular momentum vector pointing out of the screen. Yeah. And since the angular momentum vector is constant, this 2D plane is fixed. It doesn't change in time, and therefore position and velocity and momentum will always lie in the same two-dimensional plane, which doesn't change in time. So effectively, the motion of the system becomes two-dimensional. So effectively, the motion becomes two-dimensional. i.e., confined to the plane spanned by the initial R and P. So if you have a central force, that simplifies matters a lot because angular momentum is conserved, and one of the consequences of that angular momentum conservation is the fact that the motion becomes effectively two-dimensional. Then I'd like to show you a second consequence, direct consequence of angular momentum conservation when you have a central force. And this is the so-called area law. The area law, what is this? I'm sure you've heard about this before. It's actually one of Kepler's laws, and the idea is the following. Let me draw again a coordinate system, and we learned previously that motion of the system, when you have angular momentum conservation, you have a central force, motion of the system is constrained to a two-dimensional plane. So let's say that this coordinate system now spans this two-dimensional plane in which the system moves. Let's say the body is somewhere here with position vector r. And now after some time dt, so this is a clock, dt, the body moves a certain distance. Let's say the body moves here, and this distance vector that it moves in infinitesimal time dt, this is given by its velocity r dot times dt. Now this gives you a triangle here, This is the area. If you imagine that there's the origin and the body are connected with a string, and then say an elastic string, and now the body moves this infinitesimal distance, and then this string sweeps over this red area. Let me call this area dA. Okay. Now, what is the size of this area? dA. Now, the area of the triangle, this is 1/2, and then the absolute value of the vector product of R with R dot dt. So I take these two vectors that I drew, a position vector R and this infinitesimal distance vector R dot dt, take the vector product, and you all know the absolute value of the vector product is the area of the parallelogram spanned by the two vectors, and the triangle is just half of it. But now you know that R dot, that's the velocity, this is 1 over mass times momentum. So this, I can write this as momentum times 1 over mass. But then you have, in there you have the vector product of position vector R with momentum, so R cross P. And R cross P is L. So in fact what you have here for the area, this is 1/2, then the 1 over m I can take in front. So I have 1 over 2m. And then I have the absolute value of the angular momentum vector times dt. And this implies that dA over dt, so the area per unit time over which I sweep with my connecting string, this is 1 over 2m times the absolute value of the angular momentum vector. But the angular momentum is conserved when we have a central force, and therefore, in particular, its absolute value is also conserved. So this is a constant. So in fact, another consequence of angular momentum conservation is that in equal times I sweep over equal areas. And you probably recognize this as one of Kepler's laws. We'll come back to that when we talk in more detail about the Kepler problem. Next, I would like to talk to you about the concepts of work and power, and also introduce the notion of kinetic energy, which previously we had only for motion in 1 dimension, and now I introduce it for motion in 3 dimension. So we have here a section on work, power, and kinetic energy. When you have a body that you move from some initial position R1 along some curve C to a final position R2. And along this trajectory, there are forces acting on this body. For example, at this position here, there might be a force acting in this direction. So here you are at position R of t, and at that position, the body experiences force F. And then it moves on after some infinitesimal time dt, it moves by an infinitesimal distance vector dr, which is r dot of t dt. Yeah? Now for this infinitesimal piece, work or on that infinitesimal piece of the trajectory, work is performed on the mechanical body, and the work performed on the body infinitesimally, this is the force scalar product with this infinitesimal distance vector. So I'm sure this is familiar to you, the definition of work. It's the scalar product of force and distance vector. Now the total work done along the trajectory from R1 to R2 along C, that is the integral from R1 to R2 F scalar product with dr. And here it is important to note that in general, the total work done on the system, mechanical work done on the system, may depend on the specific trajectory that you choose. So you might go from R1 to R2 along a different path, and then in general it may happen that the work that you perform is different. So this is important to know. In general, the work may depend on the path. What is the work that you do per unit time? So on this infinitesimal blue section that the body travels in the time interval dt, a certain work dw is performed, and the work performed per unit time, the work is scalar product F with dr, and this per unit time, you recognize this is the velocity, so you have F scalar product with r dot velocity, and this work performed per unit time is called the power and defined and labeled with the letter capital P for power. Maybe just as a little side remark, the units of these various quantities, the work is force times distance. So the unit is Newton times meter, and the Newton itself is kilogram times meter squared per meter per second squared, so together you have meter squared per second squared, and this is the joule. And for the power, you have the unit joule per second, and this is the watt. So much about work and power, and I need an extra page for the kinetic energy. As in the one-dimensional case, start from the second axiom, force equals mass times acceleration, and as in the one-dimensional case, you can take You can multiply this, and in this case it becomes the scalar product with the velocity, both on the left-hand side and on the right-hand side. Now on the left-hand side, force scalar product with velocity, that's what we just defined as the power. And on the right-hand side, this can be written as the time derivative d over dt of, sometimes I press buttons that I don't want to press. So this is m over 2 r dot squared, which you all know as the formula for the kinetic energy. So this here is the kinetic energy T. So you see the connection here between power and kinetic energy. The power is responsible for the change in time of the kinetic energy. Yeah. Or exerting power on a system changes its kinetic energy. So we've talked about work, we've talked about power, we've talked about kinetic energy. What's missing? We talk about the various forms of energy. That is potential energy. Now again in the three-dimensional case. And here what I would like to develop this in a slightly more different, more general fashion than in this very simple one-dimensional case. As a first step, I would like to introduce the distinction between conservative forces and dissipative forces. So the force acting on my body is composed in general of two parts, one which I shall call conservative and another part which I would like to call dissipative. And these dissipative forces, we've already encountered a few examples, also on your problem sets. Typically, these dissipative forces are velocity dependent. The converse, however, is not true. Not every velocity dependent force is automatically a dissipative force. One example is the Lorentz force, the magnetic force, which is velocity dependent, but it's clearly not dissipative. Yeah? Now, what distinguishes conservative forces from other forces? Let's consider the power exerted on a body by a conservative force. So the power exerted by a conservative force is, as before, the scalar product of the force with velocity. And if it is possible to write the power as a total time derivative of some function u, which depends on position. Yeah? If that is possible to write the power exerted by a force in this way, then the force is conservative. So force is conservative if the power exerted can be written as minus du over dt. Yeah? This is not true for all forces, and therefore the forces for which this is not possible, they are then subsumed under this heading of dissipative forces. Now, what happens to the kinetic energy of a body under the influence of these forces. So we consider the change of kinetic energy. We learned before, this is just the power, so this is force scalar product with velocity. And then we have the contribution from the conservative force, which can be written as a total time derivative minus du over dt, some function u. And then we have a remaining contribution from the dissipative forces. So this is the dissipative force scalar product with velocity. This implies we can take the function u, which we recognize again as in the one-dimensional case as a potential energy. We can take that to the left-hand side, and we can write the time derivative of kinetic energy plus potential energy. And this is now in general not zero anymore, but it is equal to the power exerted by the dissipative forces. In the one-dimensional case that we considered before, we had excluded dissipative forces. We've done that implicitly by saying that our force is not allowed to be time-dependent explicitly and not allowed to be velocity-dependent. And in this way, implicitly, we excluded all dissipative forces, and therefore on the right-hand side we had zero. But in the more general case, we have, on the right-hand side, we have this contribution from the dissipative forces. So just to summarize, this is the kinetic energy, this is the potential energy, and this is the total mechanical energy. And this total mechanical energy is in general no longer conserved. It can change by dissipative forces, which means, of course, we still have overall energy conservation. This simply means that mechanical energy is transformed into non-mechanical forms of energy, like heat, for example. Yeah? Okay, now another way to characterize conservative forces is by saying, well, up there we said we can recognize that by the fact that the power can always be written as a total time derivative of some function u. Another way of phrasing it is to say that forces are conservative if the total mechanical energy is conserved, and therefore the sum of kinetic energy and potential energy is a constant. So we can say forces are conservative, i.e., there is no dissipative force if and only if T plus U is conserved. In the following, I would like to focus on conservative forces and explore in a bit more detail the consequences that has. So let's focus here on conservative forces. Now let's remember the property of conservative forces. The property of conservative forces, the distinguishing property of conservative forces, is the fact that the power exerted by these forces can be written as a total time derivative of some function u of position. And we can apply the chain rule, we can also write that as minus the gradient of u scalar product with r dot. Okay? Because U is not explicitly time dependent, but it depends on position, which in turn is a function of time. So by chain rule, we can write it in this form. Now, looking at this equation, so the left part and the right part, you might be tempted to conclude that conservative forces always have the form minus gradient of some function, some potential u of r. However, that's not quite complete, because the conservative forces may include other terms as long as their scalar product with the velocity vanishes. So in general, you may have also contributions of the form velocity vector product with some other field, some vector field. Such a term is always perpendicular to velocity, and therefore the scalar product with velocity vanishes, and it doesn't affect the defining property of a conservative force, namely that the power is the total time derivative of u. So we can always add terms of the form velocity vector product with some vector field B, and you recognize this is precisely the form of the Lorentz force up to a multiplicative constant. So this is the Lorentz force, for example. Nevertheless, the first part is what we would like to focus on. Yeah? So focus here, no velocity dependence. So at this point, from here onwards, we would like to focus on forces, conservative forces, which can be written as a gradient of some potential. So F can be written as minus the gradient of some potential, and it's conservative. Mathematically, what does that imply when you can write a vector field as the gradient of a potential? It means that the integral of the force field along some path from some endpoint R1 to R2, that this is path independent. Right. There's one piece in between that I wanted to add, namely that the curl of F vanishes, sometimes written like this. And in fact, these implications go both ways. So these are all equivalent ways of characterizing the force. And if we exclude velocity-dependent forces, then you can use either of these three statements to characterize a force as conservative. Just as a little side remark, I'm sure you know this from vector analysis, so I just want to indicate it briefly. How can you understand the first connection here, that if the force can be written as a gradient, then the curl vanishes. You can check that, for example, for a simple component. You can say that the z component of the force, this is minus partial derivative with respect to z of the potential, and likewise for x and y. And then you can calculate, for example, of the curl. Let's say you calculate the x component. This is by definition dy fz minus partial z fy, and then you insert, for example, the z component, that's partial z of u, and then for the second term you have the y component, that's partial y of u, again with the minus sign, and you see the two terms cancel because you can swap partial derivatives, and this is equal to 0. Yeah? This is behind the first equivalence, and now behind the second equivalence is Stokes' theorem. Stokes' theorem says that when you have here a closed loop, and here is an area here, then a path integral along a closed loop, this equals an area integral dA times the curl of f. And this Stokes' theorem is behind the second equivalence.